Hi, Mohammed here. So we've been working on some pretty cool stuff for this project, and I think you should have a look.
Hello, my name is Tommy Foland, and here is our rocket system fully designed in SolidWorks. So as you can see, our rocket system is broken into all of its separate components, and this allows for quick iteration and design changes to be implemented into our system. It's about 4 feet long, has an ogive nose cone. Our body tube is Bluetooth 2.0, and our fins are just made of plywood. So I'm going to go ahead and blow this up really quick and kind of show you what our entire system looks like. And there is every component of our system.
So the goal of the flow sim was a basic sanity check on our aerospace calculations and to ensure that there were no pressure buildups in strange spots on our geometry. And as you can see by this cutoff for the plot, our pressure buildup makes sense at the nose cone as well as when it encounters our fins. And there's some slight variations when it encounters changes in area as well as disturbances from the launch lugs that we have. And overall, what we saw was pretty nominal. We were also able to get a flow velocity outside of our rocket, which demonstrates the flow of our rocket motor, and the discoloration in there you can see is due to the flow from the propellant, and nothing is out of the ordinary. And it also just continues to show how everything we're seeing is nominal, and we were good to continue to testing.
Good afternoon, everyone. My name is Juan, and today I'll be talking about the modal analysis, structural analysis, and thermal analysis of the rocket. These analyses were done in SolidWorks based off of the model that Tommy spoke about earlier. What you see here on the screen are the first 6 natural frequencies of the rocket. The rocket is going to move through these natural frequencies very fast, so they're not much of a concern. They also have low periods, so they're not going to be taking as much time. What you see are the exaggerated movements of the frequencies just to show what their actual shapes are, but they're not of a concern. The reason behind that is because of amperes. This is SolidWorks' built-in function to display maximum displacement from a certain starting point. These are all relatively small compared to other amperes values, so they're not of a concern. The structural analysis is based off of the rocket resting on the launch rail before it's taking off. The first picture that you see on the left is the maximum displacement that we're going to see. That is because of the moment happening here at this launch rail. We're going to see a maximum of 1.3 inches, and that will be the fin rotating this way. However, we're not actually going to experience that due to the bottom of the rocket hitting against the launch rail itself. The middle is the von Mises stresses that we're going to see while the rocket is resting, and they are not of concern either due to these being below the critical value for the cardboard that we have. The max von Mises stresses that we're going to see are at the rail buttons and at where the fins meet the body tube. The last one that you see here is a strain, which is also negligent, and we're going to see max strain at the launch buttons. The thermal analysis, the only concern that we had with it was the rocket motor here, because it can reach up to 425 degrees Fahrenheit at max impulse. However, it is not a concern for everything else in the rocket due to the insulation that the motor itself gives, the motor casing, and the cardboard tube that we have it put on when it's in the rocket.
Hello, my name is Joan Nardon, and I will be providing an overview of the model rocket on OpenRocket, a flight simulation and model rocket design software that was a very crucial part of the analysis of pre-eliminatory research to satisfy the requirements of the 2000 feet apogee and trying to transport and protect the payload throughout the flight. The design fit the desired stability between the 1.5 to 3 caliber range. Right now, the Stability is at 2.64 caliber. The body tube is a 3-inch in diameter, around 1,513 grams with the motor, 49 inches in length with the center of gravity at 31.89 inches and the center of pressure at 40.1 inches. Keeping the center of pressure under the center of gravity, which is very crucial to keep the stability of the rocket. The current motor configuration the team currently has is a I-218R. That is a solid motor, commercial off the shelf, that is a 38 millimeter in diameter. Comes with Aerotech grains and is a reloadable motor system. The simulations with the I-218R show that they can reach of an apogee of around 2,236 with an approximate 1.5 second burning time and a safe landing of a vertical velocity of 20.8 feet per second.
Hi, my name is Padma Sharma. I'm going to provide a brief overview of the electronics running on our rocket. We have two electronics, the Transolve Mini Beep X and the Featherweight Blue Raven altimeter. And here is a video of the test that we conducted for the Featherweight Blue Raven altimeter. This is a screen recording of the app that they developed, which allows us to monitor temperature, altitude, and acceleration data. About the Transolve Beep X, it will produce a loud and very audible beep that will allow us to locate the rocket upon landing, and the Featherweight Blue Raven altimeter will satisfy a requirement of having a commercial off-the-shelf component that will provide and record altitude data. That is all. I hope you enjoyed this.
Damn, son, where'd you find this?
Hey Mohammed here. So I'm going to be talking about some of the choices that we've made in selecting the parachute and how we went about it. So firstly, we had to make sure that our descent velocity had to be less than 30 feet per second due to our requirements. And we have found, first of all, a 58-inch parachute with no spill hole, which gave us about 14.22 feet per second, which is good, give or take. But the next one we have is a 48-inch, which will take up less space in our compartment inside the rocket body, which will give us about 17 feet per second. And all of this is calculations for considering it's a round parachute and not an octagonal or square parachute. And then next one down here is a 36-inch parachute, which gave us about 22.914 feet per second. But then again, this is also for a round parachute, which isn't pretty easy to find for that small of a size. Then the next one, which is even more precise, is the octagon parachute hand calculation, which will show us the 48-inch octagon chute to be about 18 feet per second, and then for a 36-inch to be about 24.15 feet per second. So based on all this, we've decided to go for a 48-inch octagon chute, which is nearly a round parachute based on the calculations and the things that we've seen in apogee. So yeah, we decided to go for a 48-inch or a 4-foot parachute for our recovery system.
I'm going to now show you our autonomous payload loader. So our system here kind of utilizes a gutter system that basically is voice activated by electronics that are mounted on this back stand, and this gate will open and allow our payload to actually slide down our gutter and load into our rocket. So here is a brief animation showing that. So there we go, the gate opens and our ping pong balls are free to slide down the ramp into our rocket.
Here's our autonomous payload loading mechanism, where a turn of a switch outputs 12 volts from two 6-volt batteries in series into a car charger that outputs 5 volts to a Genie Wi-Fi control LED system, where Wi-Fi control devices can turn on and off any of these manual switches, which will allow the servo gate to open or close.
Hey Siri, open Sesame.